Southern Spectroscopic Survey Instrument. So I'll start out with some basic context. I know there are a lot of students here, so I'll try to explain the things that we know should be going on in the 2020s. Explain a little of the basics of spectroscopy, because that's going to be a real focus of this discussion. And then I'll talk about two reports. One done under the auspices of the American National Science Foundation, funded by the Kavli Foundation, that brought together the National Optical Astronomy Observatories, LSST, and the community to try to determine what instrumental capabilities should be prioritized. And a second report that came from the U.S. Department of Energy, or a team that they convened, focused on what can we do in the next decade that will be complementary to and build upon DESI and LSST, and potentially bring us to even stage 5 dark energy experiments. So to remind you, LSST is under construction now. It's an 8-meter diameter wide field telescope. Effective area is more like a 6.5 meter because of the very unusual, very fast optical design. You can see that there's sort of an inner region of the mirror that's actually got a different curvature, that's a tertiary mirror. So you lose that area in your sky coverage. And so LSST will get very deep imaging in 6 filters, U, G, R, I, Z, and Y, by getting short exposures, back-to-back 15-second exposures. With this very fast beam, it gets a wide area, so 10 square degrees at a time. With that sort of exposure time and area, it can cover the visible sky every 3 or 4 nights. And so LSST will start in 2022, getting imaging on the sky, and just keep going for 10 years. And at the end, you have more than 800 of these short visits per pointing. And that allows you to combine all the photons and go very deep. But you can also look at the individual frames and see everything that changed from night to night. So there's a wide variety of science cases for LSST. It was the top priority from the last decadal survey in the United States that set the priorities for the next decade in astronomy. First and foremost, the telescope was designed for cosmology, looking at dark matter, dark energy in particular through weak gravitational lensing, but also through the large-scale structure BAO, through galaxy clusters, through supernovae. It'll provide tests of general relativity, mostly by looking at consistency between, for instance, the lensing signal and the distance measures from supernovae or at large-scale structure. But the other science cases span astronomy. So LSST will give us a detailed map of the Milky Way, extending out to tens of kiloparsecs. We'll be able to get parallaxes for pretty faint stars. Basically, where Gaia ceases to be effective, LSST picks up and can continue to get Gaia-like parallaxes for fainter stars. So we'll get a 3-dimensional map of the Milky Way, as well as having distances to the stars. You'll have color information. You'll have proper motions from that 10-year baseline to see how they move across the sky. So that's going to really revolutionize our understanding of the structure of the Milky Way. Furthermore, we'll find everything that changes from night to night. We really don't know what LSST will find. We've never had a transient survey that could go this deep, this fast on these sorts of cadences. Because every time, every 30-second exposure is going to about 24th magnitude for transients. And LSST will release alerts within 60 seconds of an image of everything that changed from the previous images of that area of sky. So we're going to have an overwhelming number of transients to sift through whole new classes of objects, I'm sure, that we haven't discovered before. We'll have information on from LSST. And then finally, LSST will be very relevant for solar system astronomy as well. You can do things like look for Kuiper belt objects, but in particular, LSST will be quite effective for finding near-Earth asteroids. So something like 80% of Earth-crossing asteroids big enough to destroy a city will be found by LSST at the end of the survey. And so we can eliminate much, though not all, of the risk of something coming to get us that we don't know about through the LSST survey. The LSST is a big focus of my science, and it's a big focus of these reports because it's the largest national project happening in the U.S. over the next decade. So DESI, in contrast, is not a new telescope. It's taking an existing telescope, a telescope that's more than 40 years old, and putting a state-of-the-art instrument on it so it can do things that no other telescope can. So in particular, it's going to add spectrographs that cover the full optical wavelength range, so from below 4,000 nanometers to about a micron, onto the 4-meter Mail telescope at Kitt Peak in Arizona. And so what it'll do is it'll put at prime focus on the telescope, so up at the top end, a set of robotic fiber positioners that take light from 5,000 fibers and channel them down, that's the yellow lines here, to a set of spectrographs in the basement of the building. So in this way, we'll be able to get spectra of 5,000 objects at a time over an area of more than 7 square degrees. So the field of view is not that different from LSST. And so this is a very efficient instrument in particular for looking at baryon acoustic oscillations, for looking at the growth of the universe by using the standard ruler imposed at the CMB epoch by the acoustic oscillations in the photon baryon plasma. So in the end, DESI will get redshifts for more than 25 million galaxies and quasars, most of them at redshifts of 0.5 to 3.5, but there's also a low redshift survey covering Z less than 0.5. Over 14,000 square degrees of sky, so that's a third of the visible sky. LSST is 20,000 square degrees. One difference, though, is LSST is in Chile, DESI is in Arizona, so they overlap between these areas is only about 4,000 square degrees. Only about a quarter of the area is common to both. So DESI is intended to be a stage 4 BAO experiment, so about 10 times better than the current state of the art, and it's approaching quickly. It should start around 2019 and continue through 2024 as our best current estimate. So this is just illustrating how DESI will constrain cosmology. We measure the distance using the standard ruler, using the fact that we have an object of known co-moving size, the baryon acoustic oscillation scale. We can measure its apparent size in angle or in redshift at different redshifts. And in so doing, we're able to get constraints on the rate at which the universe was growing. And that's what this plot illustrates. You can see, particularly around Z of 1, DESI has really exquisite precision. And the regime where it's doing worst at sort of Z of 1.5 to 2 is where projects like Euclid and WFIRST will do very well. So DESI is highly complementary to those projects. And so, of course, the growth rate of the universe, or the distance, measures how the universe has grown over time and depends on the components of the energy density of the universe, including the equation of state of dark energy. So we can hope to get constraints on what the dark energy might be if it's not a simple cosmological constant through DESI. The BAO technique is very nice because it's relying on measurements of redshifts, which we know how to calibrate, angles. We've been known how to measure angles very accurately going back to the ancient Greeks. So the systematic uncertainties are pretty modest in DESI measurements. In contrast, LSST has much more constraining power, but we have to worry more about systematics as well with the LSST techniques. So the other thing that's going to be happening, not just in the US, but around the world as we enter the next decade, is we expect to enter an era of extremely large telescopes. And there are three major projects ongoing right now. The one at the left is the giant Magellan Telescope being built in Chile. At the center is the, actually that one is the European Extremely Large Telescope, a 40-meter telescope being built in Chile. And then at right is the 30-meter telescope, which we thought was going to be built in Hawaii. It might be the Canary Islands instead. That's still Depends on politics in Hawaii, so we'll see. And these telescopes are very different from LSST and DESI in that they have very large collecting areas. So they're great light buckets for collecting photons, but they have very tiny fields of view. So if you want to do surveys, if you want to collect a fair sample of objects in the universe, that's very difficult with these telescopes. Getting large samples will be very difficult because, if you're a PI at an institution with access to, EELT, you're lucky to get a night every year. There's only so much you can do in that time. All of these telescopes are under construction. None of them have all the money to proceed. So how that works out is going to be interesting. But I think it's reasonable to expect that at least one of these telescopes will be done by the late 2020s with a basic instrument suite, not the full suite of instruments you'd find at a telescope like CAC or VLT, but some sort of adaptive optics imager, some sort of multi-object spectrograph, some third instrument in each case will be on these telescopes. But it's going to be the instruments for these telescopes can be $100 million. So it's it's difficult to get the money to build the telescope and build instruments. So this is all the context. I want to step back and just review what we measure with telescopes because I'm going to focus on a particular type of measurement, spectroscopy, and I want everyone to be comfortable with that. So there are three basic types of things we measure with an optical telescope. One is positions of objects, so that's astrometry. That's the most ancient type of astronomy going back to the ancient Greeks. Astrometry is still important for things like measuring parallaxes to stars with LSST, or finding asteroids and measuring their orbits. The second type of data we collect is photometry. It's generally coming from the same images as we get astrometry from. With photometry, we're not just measuring positions, we're measuring brightnesses and potentially measuring colors and shapes of objects. And photometry, too, is very ancient. The Greeks defined a magnitude system that basically we still use. And so LSST is going to perform astrometry and it'll perform photometry. The third type of data is spectrometry, where we measure the brightness of an object as a function of wavelength. And so spectrometry is the newest of these. It really dates back to the 1800s. It provides by far the greatest amount of information. So for instance, for galaxies, we can measure redshifts and chemical compositions, star formation histories. For stars or the interstellar medium, we can measure temperatures. Astrophysics grew out of those first spectroscopic measurements. The Astrophysical Journal emerged from that early spectroscopy. And so spectroscopy really is our best handle on trying to understand the physics of the objects we're looking at. And spectrometry generally relies on instruments called spectrographs. And I'll just sketch for you how those work. So we start out with a telescope. The telescope collects light from an object. But we face a problem that the objects we're interested in are often fainter than the night sky. So if you just take all that light and disperse it, what you'll see is dominated by the night sky. So we put something that masks out most of the sky. Either we put a little slit over the object, a hole in a piece of metal, or we put a fiber head, the tip of a fiber optic cable, over the object with a robotic positioner to collect light just around the object we're interested in, and potentially light above and below if we're using a slit to allow us to subtract out the sky signal. So that light we then pass over a diffraction grating, in some cases passes through a prism, and that then gives us a series of images of the object, one image at every possible wavelength. So I've illustrated that at the bottom with these color images, but of course wavelength is continuous, so those all blur together. So it looks something like that gray region you see at the bottom when you look at a real spectrum on an instrument. And then we sum up the light over the object, sum up the light in the y direction on this sort of image, and that gives us total flux as a function of wavelength. And so that's basically what the spectrograph does. And the real advances coming in the in the next decade with LSST are going to be in imaging, but with DESI we're making advances in spectroscopy, and that's the place where we can make the biggest gains into the next decade. So basic types of spectrographs we'll talk about, MultiFiber spectrographs primarily. So those take optical fibers, fiber optic cables, the same sorts used in telecommunications, and position them at the positions of objects in the focal plane. In some cases this is done by hand. For Sloan this is done by hand, people plugging little fiber optic cables into metal plates at the right positions. For DESI we do it robotically. And then those fibers carry the light to the spectrograph, and then the light gets bounced off the grating, dispersed, and you get spectra. This is just illustrating at the right what some of the data there looks like. Most of what you see, these vertical features here, are features that have the same wavelength on every spectrum. So those are emission lines of the night sky. And in fact, most of what you see in this spectrum is light from the night sky. You have to subtract all of that off. The horizontal lines are alignment stars, so those are bright. The objects we're interested in, the galaxies, are much, much fainter than that. So there's significant data processing issues because the night sky, where these skylines are, they can be easily 100 times brighter than the galaxies of interest. And so even when you subtract them, there's Poisson noise, if you don't subtract them perfectly, there's residuals to deal with. So spectroscopic data analysis is not easy. Imaging data analysis isn't either, of course. So the other sort of spectrograph that's becoming more and more common is the integral field unit. I'll talk a little bit about IFUs. So an integral field unit is an instrument that can get a spectrum at every point of a field of view. So you can imagine an image, you have a set of pixels on a galaxy. With an IFU, at every pixel you have a spectrum. So you're getting a data cube. You're getting a three-dimensional set of what is the spectrum at every position, or equivalently, what does the image of the galaxy look like at every possible wavelength. So it's no longer blurred together in the same way it is with the standard spectrum. So there's a variety of technologies you can use. You can put a fiber at every pixel. You could use lenslets to redirect the light. You could use an image slicer that sort of turns an image into a series of slits and then redirects the light so those slits are stacked on top of each other on the focal plane. But in any of these technologies, you're getting one of these data cubes. And in the end, you can reconstruct an image of the object at any wavelength. So here at the left is just illustrating the image slicer technology. You can reconstruct the image at any wavelength, or you can get the full spectrum and do the full astrophysical analyses at every pixel. And so these are extremely powerful instruments. They generally have small fields of view. They're most commonly being used in the next generation with adaptive optic systems in the infrared, where you can make the galaxies as small as possible, make all the objects as small as possible, so you get as many resolution elements over an object as you can, thanks to the high resolution from adaptive optics. So that's all background to what I'll be talking about. So there are two reports I'll be talking about. The first was released a couple of years ago from the U.S. National Research Council. It's a report on a strategy to optimize the U.S. optical and infrared system in the era of the Large Synoptic Survey Telescope. What that means is what sort of telescopes, what sort of instruments, what sort of capabilities do we need available to the U.S. community to complement LSST. And this report looked at a lot of things. It made a set of relatively broad recommendations. One thing that was nice about the report, but also has disadvantages, is every piece of input they got referred to in the report, encompassed in some recommendation. But this sort of levels out prioritization, so it's hard to tell from the report what's the first thing you should do, what's the second thing you should do, and so forth. And so late last year, the National Science Foundation asked NOAO and LSST to work together to produce a new report that was intended to really quantitatively look at what we need to complement LSST. So the report is organized around half a dozen science cases with them. How many nights do you need on an 8-meter telescope with this sort of instrument, for example? And it's intended to allow the community to assess and prioritize what sort of resources we need, which includes new telescopes, new instruments, or new software infrastructure that could fulfill those cases, and try to identify high priorities for future investments. And so it's intended to provide input not just to the National Science Foundation, also to private funding sources and observatories. They'll have a community review they can point to showing what capabilities there's the most need for when setting their priorities. And so the report was made possible by a grant from a private foundation, the Kavli Foundation. So we put their name first. So the report was led by Joan Najita at the National Optical Astronomy Observatories in Tucson, and Beth Willman, who's the Deputy Director of LSST. And they convened an organizing committee that I was on. So basically, late last year, we sent out a call to the community for inputs on what they felt was needed to maximize science with LSST. Then we set up a set of 6 study groups that last spring came up with quantitative estimates of what capabilities we needed. In May, we all met together at Biosphere 2, which is a sort of an ecological laboratory in Arizona, to try to discuss what everyone came up with, try to see where there were overlaps, where there were cases that needed unique capabilities. And then over the summer, we finished off the report. It was released in October. So here's the archive link. I can send an email with it if it's helpful later. So the report exists. More than 50 people contributed. There a lot of thought went into this report. So my focus was on the science case for cosmology. So how do we enable cosmology measurements in LSST? But I'll just tell you about the other science cases too. So first of all, using small solar system bodies, so asteroids and comets, to understand solar system evolution. A very focused science case comparing rotation and magnetic activity in stars in the galactic field and in star clusters. So this was kind of unique. We were all asked to come up with single compelling cases, but only one working group was able to limit themselves to that. So that's a very detailed case worked out in full. A third working group that focused on things like dwarf galaxies in the Milky Way, focused on studying galaxy formation, dark matter, gravity in the local group, including the Milky Way and local dwarfs. A fourth working group focused on transients, including supernovae. A fifth focused on galaxy evolution, looking at AGN reverberation mapping, looking at deep surveys of galaxies at Redshift 2, looking at absorption line studies of the three-dimensional structure of gas in the universe. And the cosmology cases I'll talk about in a little more detail. So the cosmology study group was about a dozen people who contributed, to which thanks. So the case that we spent the most time is for photometric redshift training. And so what I mean by that is using sets of objects where we know the spectroscopic redshift so we can train algorithms, improve algorithms that map from observed colors from LSST to redshift. Because LSST only has these 6 colors, we won't have detailed spectroscopy, so we'll have to rely on photometric redshifts, photo-Zs, for most objects. And so this plot is illustrating sort of the for weak lensing in blue, for BAO in red, and for the combination in purple. In LSST, we have confidence, just with what we know about galaxies now, we can achieve errors of 0.05 times 1 plus c. to 5% errors. However, if you take a situation where you know the spectra of galaxies perfectly, you know, the ensemble of spectra of galaxies, which is what you should get if you had perfectly trained templates, then LSST can achieve performance of 2% to 2.5% on photoses. So that's about a 40% gain in figure of merit when you put it all together. So that's non-negligible. It's the same as, you know, it's almost like having a second LSST. So a training campaign that costs a lot less than LSST but gives you redshift spanning the properties of LSST galaxies will be extremely valuable. And so for photosy training spectroscopy, we set a set of requirements in this report that are based on analyses we've done before, in particular in a white paper I led a few years ago. So first of all, we want sensitive spectroscopy, so good enough to measure redshifts at very high rates, or at least 75% rates, for about 30,000 faint objects. So 30,000 is enough to reduce the errors in the training, but we need to go to the magnitude limit of LSST, which is I of 25.3. This is, so if you compare to surveys like Deep 2, BVDS, this is about 2.5 magnitudes deeper, which means 100 times the exposure time. So if you have the same telescope and the same instrument. So, you know, 100 hours at Keck to get 75% redshift success rates. This is pretty daunting. That's a lot of nights. And that's, you know, at Keck you would get 100 at a time. Getting 30,000 is a lot of hours. So what you really need is large aperture and long exposure times to have any hope of reaching those magnitude limits. But you don't want to do this 100 at a time, because that would be then, you know, 300 pointings at 100 hours each. It adds up quickly. So instead you want a high multiplexing. So you want to be able to observe many objects at the same time so that we can achieve that 30,000 goal in, you know, in a reasonable amount of time. So we want to get coverage of the full ground-based spectral window if we can. The broader the wavelength window you have, the greater the chance you have of seeing two spectral features, which is what you need to get a secure redshift. So ideally we'd start below 4,000 angstroms and extend to 1.3 or 1.5 microns. Our minimum requirement is to extend to 1 micron, which you can do with CCD technologies. We require significant resolution, so resolutions above 5,000 at the red end. That requirement is set because if you have that resolution, as you go to redshifts above 1, the last emission line that's in your window is the oxygen 2 3727 angstrom doublet. So it's actually 2 lines, and with enough resolution you can tell it's 2 lines. You see those 2 lines, you measure their separation. It's unique for O2, so it gives you a secure redshift. It gives you 2 features from just that 1 doublet of emission lines. So if you have that resolution, you can get a 1 feature almost redshift out to redshifts above 1 with the limiting redshift set by the end of your spectral window. So for 1 micron, you go to about Z of 1.6, for instance, with this technique. So we need significant field diameters, so we don't want to just have lots of spectra in a very tiny area of sky like the ELTs give us, but we rather would have a diameter of at least 20 arc minutes. A full moon is 30 arc minutes across for comparison. And so we want to do that because that will span multiple correlation lengths, which allows accurate clustering measurements, allows us to do galaxy evolution science with the same samples. It also helps to mitigate sample cosmic variance. And then the final requirement is to observe a relatively large number of fields, at least 15. Again, to mitigate sample or cosmic variance. If you look in the same area of sky and get 30,000 objects in the same area of sky, your redshift distribution will be imprinted with the fact that that area of sky happens to be overdense at a certain redshift and underdense at a certain redshift, and systematically you'll get biased. So if instead you try to get a fair sample of the universe, that bias is mitigated. We'd like at least 15 fields because that's enough that you can not just measure the densities, but you can measure scatters very well. With 15 samples, you can throw out fields that are outliers with samples that large. So those requirements lead to a set of requirements for spectrograph. But in the Kavli study, we identified a wide variety of cosmological studies that would be made possible by the same sort of instrument. I think the most important of these is to inform and test models of intrinsic alignments between galaxies that are near each other on the sky. So the weak lensing signal you're looking for is an alignment of basically the directions of ellipticity of galaxies that are near each other on the sky. Unfortunately, galaxies that are near each other in 3 dimensions, because they're suffering similar tidal forces, amongst other things, tend to have aligned directions, aligned axes. So that can masquerade as a weak lensing signal. So we really need to understand this effect very well for it not to limit our weak lensing cosmology measurements. So you don't need high precision redshifts, but they need to be better than photoz's, so you can tell which galaxies are physically close enough to each other that they should align. You want to span relatively large fields, so more like degree scales than 20 arc-minute scales. And you want tens of thousands of objects for surveys that can help you understand intrinsic alignments. So that's one project. Second that's been talked about is how do we make better models of how we should or shouldn't modify photo-Z priors in fields where there's a cluster. So there's been lots of discussion of how you might do this, but we want to not be biasing our weak lensing inference if you do this. So you could do surveys on cluster lines of sight to test your photo-Z algorithms that incorporate this sort of thing. The same sort of data can look at the cluster galaxies simultaneously and test theories of modified gravity by looking at how fast galaxies are collapsing into the clusters. The galaxies that are just starting to fall in provide a sensitive probe with gravity. Another cluster case is looking at kinematics of galaxies and clusters that just went through mergers, like the famous bullet cluster, which again will be sensitive to dark matter properties on smaller scales, things like self-interaction. And then finally, performing detailed tests of blending effects on photometric redshifts. In regions where you have HST data, you know which things are blended, which aren't. You can do tests of how do the photo-Z algorithms perform, how do we try to throw out objects that might be potential blends empirically. So one cosmology science case has very different needs, which is strong lens cosmology. For strong lens cosmology, you're relying on the fact that the time delays in a strong lens system depend on cosmological parameters. It depends on the difference in distance between different lines of sight that eventually converge to us. Those different lines of sight, the different images of a multiply imaged object actually have different path lengths. And so if you see something that's changing with time, like a quasar or a supernova, that source will brighten at different times in different images. And from those differences in distances, as well as extremely accurate positions of measurements of redshifts and positions, you can actually then determine cosmological parameters in the end, particularly get constraints on the Hubble parameter, especially. And so the image here is just an illustration of a case where this happened. Supernova Refstall, the first identified strongly lensed supernova, where the supernova was seen first in one image and predicted to appear at another position later, and lo and behold, late in 2015, it did appear where it was predicted to. And so then, from those differences in appearance time, you could get a time delay in constrained cosmology. And so this accurate measurement of position and redshift is best done with adaptive optics. And so if you have an IFU spectrograph, you can do this all simultaneously. Some of the objects are bright enough you can do them with an 8-meter telescope. Some of them you might want a 20 to 40-meter telescope. The requirements are generally a resolution of 4,000 to 5,000, mostly so you can work in between the night skylines. wavelength coverage of as much of the near infrared as you can get, 4 arc-second by 4 arc-second field of view to cover all the multiple images, and you want the adaptive optic systems to be diffraction limited so you're getting the full advantage of the diameter of the telescope and the level of detail, the level of position accuracy you can obtain. And this is a relatively inexpensive project. I'll show you the sorts of times required later for the PhotoZ training. It's, you know, months to years. Here it's 100 hours total to do 100 lens systems. And LSST will provide us with hundreds of systems that you can choose the best from. With some follow-up imaging, you could even enlarge those samples. The sort of multi-object spectroscopy, multiplex spectroscopy I talked about is also useful for strong lens systems, though, because one factor that it's useful to understand is the foreground shear along the line of sight, the effect, the lensing effect of all the other galaxies along the same line of sight. So that foreground shear can be constrained if you know the positions and masses of the redshifts on that line of sight. So the recommendations from the Kavli report were, first of all, one resource was seen as having an urgent need, but no current development path known for it. There are ideas, but nothing is moving forward, which is to either develop or get access to a highly multiplexed, wide-field, optical, multi-object spectroscopic capability on an 8-meter or larger class telescope, preferably in the southern hemisphere to complement LSST. So this is the sort of instrument you want to do this PhotoZ training. And so there are a variety of other science cases that also call for that capability. Then there were resources that are being developed now that that studies just advocating for keeping on going. These are important. First of all, to develop a broad wavelength coverage, moderate resolution spectrograph that covers the full optical and infrared window on the Gemini South telescope. This is basically an X-shooter-like instrument intended for characterizing LSST transients. So you find something new with LSST, you point this instrument at it on Gemini, it's on the same mountain, you know, you can be, you're very well positioned for it, and try to figure out what it is. And so there's a down select underway for an instrument call for Gemini to do exactly this. So, you know, the committee is endorsing that process, basically. Second activity that's going on is the development of alert brokers. So these are, you know, LSST is going to every 60 seconds, or 60 seconds after every image, give you a set of things that changed. So the alert brokers try to take that stream of input and tell you what are the interesting objects. Or you could even sort of submit queries in advance of, you know, give me any object that has a Y minus Z color bigger than 2 and brightened by 3 magnitudes compared to before, or, you know, whatever you like. That then allows people to prioritize objects for spectroscopy. And so there's a project called Antares that's sort of a prototype of this that's under development now. This was seen as we want to keep moving with these sort of prototypes. We need a capability like this by the time LSST turns on. Then there were resources that exist today that was thought to be important to keep going. So those include DECAM on the Blanco, the instrument being used for the dark energy survey, the NIFS IFU on Gemini. So DECAM is an interesting case because some of this multi-object spectroscopy you could do potentially very slowly, but you could do it by moving DESI to the Blanco. But if DECAM's tied up, you can't move DESI to the Blanco. And in particular, the solar system and stars cases wanted about 3 years of DECAM time each on the Blanco, which, you know, would set back a southern DESI significantly. And then there were seen to be some infrastructure processes that also need development. One is, how do we efficiently do follow-up programs for all these LSST transients? How do we keep everyone from looking at the same transient? How do we provide time ahead of time when you don't know when the next gravitational wave source will go off or whatever? To try to review the computing needs for the telescopes, and for LSST in particular, to make sure the community has enough computing resources, and to continue this process, to do another report, I suppose, in the future, to continue to getting community input on the planning for things that complement LSST. So I'll pause there and ask, are there any questions about the Kavli recommendations, or any questions about, I guess, the broader picture of telescopes and spectroscopy I talked about at the beginning? Okay, I guess I'll carry on then. So I'll just mention the other science cases for multi-object spectroscopy listed at the end of this slide. For studies of galaxy evolution, we need sort of an 8-meter class multi-object spectrograph. For mapping local dwarf galaxies, looking at their dark matter potentials. For mapping out Milky Way structure. For getting black hole masses through reverberation mapping. For studies of stellar rotation and activity. So almost all of the science cases from the Kavli report wanted a wide field multi-object spectrograph in the south. That's why this is a high priority. Basically to review that, so almost in parallel, so a process started a little earlier at the U.S. Department of Energy to figure out what gets done after DESI and LSST, if anything. So this is a chart I made a few years ago for the SNOMAS report, showing the set of dark energy experiments coming online with more or less optimistic timing, depending on the experiment. So in blue are imaging dark energy experiments, and red are spectroscopic experiments. And so here we are in 2016. DES is going on. HECDEX hasn't quite started. Hypersupreme is going on. PFS spectroscopy will start somewhere around 2019. The EBOS survey is going on. As we get to 2019, PFS, which is an instrument with very much the sort of capabilities we were talking about. It has 2,500 times multiplexing, coverage to 1.3 microns. It's on an 8-meter telescope. Resolution of 4,000 or 5,000 in the red. So that's coming online at Subaru in Japan. It's in the northern hemisphere, not the southern hemisphere, unfortunately. So looking further out, we have Euclid in space, LSST on the ground, and WFIRST, again in space, the U.S. Space-based dark energy experiment. And so we have this map, but there's no starts here past around 2024. And generally, we you either keep swimming or you die. If you want to have a next generation of dark energy experiments, we need to be having things that start up late in the 2020s. And so the DOE convened a set of cosmic visions panels. One was focused on the CMB stage 4 experiments. One was focused on dark matter searches, and one on dark energy studies. And so this panel on dark energy was led by Scott Dodelson, and they've released a set of reports. They're still trying to build the science cases to make concrete recommendations. So for the CMB, they released a science book recently, coming in part out of this process. For dark energy, we expect a science book in 1 to 2 years to be ready for the next U.S. decadal survey. So the process was based on a set of workshops at Department of Energy labs. The slides are available online for all of these, so I encourage you to seek them out if you're interested. The papers are on the archive that describe the basic results of this process. So the findings were, first of all, even after DESI and LSST are done, there's a lot of information left in the sky. So for a sort of a putative stage 5 experiment that measures the power spectrum in detail, the sort of inverse errors compared to today can reach, a factor of 70 times better measurements of the growth index than today, a factor of 5 better than stage 4. For neutrino masses, it can be a factor of 50 better than today, more like a factor of 10 times better than stage 4. So a lot of the cosmological parameters we're interested in, dark energy, the growth, which tests whether general relativity is correct, measurements of the curvature of the universe, the power spectrum, which gives us a handle on inflation, the sum of neutrino masses and the effective number of light particles, which gives us a handle on particle physics. All of these, there's room to make improvements. So the conclusion was, first of all, yes, we should keep going. We shouldn't stop with the stage 4 dark energy experiments. So there were a set of 5 recommendations of things to look at that could try to mine this extra information. So the first, the one case that I'll talk about in the most detail, a Southern Spectroscopic Survey Instrument. So a highly multiplexed optical and potentially with infrared spectrograph with wide field on a Southern 6 to 8 meter telescope. DESI 2, which would be the easiest of these options. It's just to keep running DESI with different target selection after the main DESI survey is complete. You presumably focus on the LSST overlap area, use LSST photoses as a prior and target selection. A third is low-resolution spectroscopy or high-resolution photometry. The idea here is to obtain not 6 colors for an object, but 20 measurements of flux at different wavelength bands, or even 100. There are technologies that have been suggested that potentially could do this. Those technologies are generally not mature, except for sort of the low-tech method of just putting filters right over your CCDs, and different filters over each CCD, and getting a different filter from each CCD. That means effectively you cut your field of view by the number of filters, but you get those filters simultaneously, is the way it works out in experimental. The fourth scenario is the least well-defined still, something called a billion object apparatus, something that could get at least 250 million redshifts. How many exactly is up in the air. And then finally, there was a recommendation to look at what could be done with 21 centimeter measurements, particularly intensity mapping, with some thought also to galaxy redshift measurements with the square kilometer array. So intensity mapping is when you measure the intensity of the H1 line on very large scales, so not resolving single galaxies, instead resolving still the BAO feature because that's 100 megaparsecs across. So you don't need very fine resolution on the sky to resolve that BAO feature. And so the idea of intensity mapping is to do something that's cheap and does just well enough to do the BAO and doesn't find individual galaxies. So there are also recommendations for new technologies. So one of the white papers on the archive is on technologies. So things like microshutter arrays to allow you to look at potentially many objects at once with spectroscopy. Germanium CCDs. So these are technologies that have been discussed that haven't been successfully implemented yet, where you take a detection layer of germanium and basically, I'd say glue, but that's not quite the right word, affix the germanium to an underlying layer of silicon that has the standard CCD electronics. So you read it out like a CCD, but it has the detection efficiency of germanium, and you can make these detectors work efficiently to 1.3 or 1.5 microns. Unlike Merck had TEL devices, they're not sensitive to longer wavelengths, so thermal radiation from your telescope is less of a background. And then the third technology that got discussed is microkelvin inductance detectors. This is a technology that potentially could give you, sort of 20 wavelength elements at once on each pixel. Right now, this technology has not achieved what you need for sort of the low resolution spectroscopy cases, but with further development, maybe it could. So just to illustrate the high resolution, oh, sorry, we're almost out of time. I should move on. So as I basically described the intensity mapping. DESI-2, again, is something with a different target selection that uses the DESI telescope. An instrument, perhaps you'd move it to the south as part of that. So my focus has been the Southern Spectroscopic Survey Instrument, so I'll highlight that. So this figure at the bottom of the page is showing the sky area for LSST in purple and the sky area for DESI in gray. And you can see there's overlap between them, but most of the LSST area is not covered by DESI. So SSSI is intended to be a massively multiplex, so at least 2,500 times, wide field, ideally at least a square degree, OIR telescope, OIR spectrograph on a 6.5 meter telescope minimum. That's the aperture where you'd have the same size spectroscopic telescope as imaging telescope, which was the scenario for Sloan, for instance. Sloan used the same telescope for imaging and spectroscopy. That's really the minimum requirement to get enough photons in a reasonable time for spectroscopy. And so SSSI is really intended to be a spectroscopic complement to both LSST and CMB Stage 4. Because those projects will be in the south, it really makes sense to put it in the south. SSSI can be done with current technologies. A lot of the DESI infrastructure can be used. The DESI spectrograph design can be used off the shelf, basically. This matches the Kavli recommendation, so there's a lot of reasons to do this. The billion object apparatus, we have no idea how to do, but you might imagine doing something with 100,000 fibers instead of 5,000 fibers, putting it on an 11-meter telescope. It's pretty easy to get cost estimates for this to get to $1 billion. If you look at projects like BOSS and eBOSS, they cost $2 a spectrum. If you're getting 500 million spectra, that gets you to $1 billion. If you're talking about building an 11-meter telescope and a complicated instrument, that gets you to $1 billion. It's hard. So basically, the roadmap for spectroscopy coming out of the cosmic visions process is DESI-2 is seen as basically being a no-brainer, relatively low in cost, could follow DESI immediately. You might try to upgrade the spectrographs to add an infrared arm to go to 1.3 microns, which would allow you to do better at higher redshifts. Moving to Blanco would be nice, but there's this question of other people wanting to use DECAM on the Blanco. And SSSI could use the DESI spectrographs to reduce the costs. Reduce the cost from something like 50 to 70 million to something like 30 to 50 million dollars. The earliest you could see doing an SSSI, given DOE budgets, is around 2026. And if you really wanted to have an efficient SSSI, you put it on an 11 to 12 meter telescope. And there are concepts, the Mauna Kea Spectroscopic Explorer, or a set of European concepts that were presented in a white paper this summer that would be well suited for an SSSI. For BOA, you need a 10-meter plus telescope, you need one of those giant telescopes, and you need to figure out how to do it. So there's a lot of R&D required, so the earliest the BOA could go on the sky would be the early 2030s, but if SSSI goes on an 11 to 12 meter, you can just swap out SSSI for BOA, put it on the same telescope, and increase your capabilities. So that would be sort of our ideal world for spectroscopy, would be steadily increasing capabilities as we go through the next decade. I guess we're about out of time. I'll just flash through where you might put an SSSI. You could do it at the Blanco if you could get access. Blanco has a slower survey speed because it's a 4-meter telescope. Magellan is actually very well suited for an instrument like this. So you could buy a new secondary for a few $1 million that would give you a spectrograph with capabilities that match or exceed those of Subaru PFS, even though the aperture area is smaller. So Magellan could match the DESI beam, so you could basically use a lot of the DESI designs off the shelf if you could get enough time on Magellan or a Magellan clone. There is a plan to build a Magellan clone in Mexico that's currently under discussion. It would cost about $75 million. It's not clear yet if that's going to happen or not. The decision was imminent last I heard, so it may have happened already. I don't know. And would be an okay host for this, but the latitude is similar to Hawaii, so it doesn't have the southern coverage that you would like. It's still better than Arizona. One option would be just to buy lots of time on Subaru, because it really has the capabilities. Again, it's in Hawaii. The biggest problem is there's a lot of demand for Subaru time. There's a lot of Japanese priorities. Once the 30-meter telescope is built, demand for Subaru should decrease. But the delays to the 30-meter telescope make this hard. Then there's the idea of the Mauna Kea Spectroscopic Explorer replacing CFHT with an 11-meter telescope that still fits in the CFHT dome footprint. That would be very interesting for an SSSI, but it's unclear whether it will go forward. So basically, if you look at scenarios for how you could do an SSSI, the cheapest option is either to upgrade DESI in the north or upgrade it and move it to the south. The disadvantage is basically the sort of photosys survey I talked about is 10 years on DESI. So you'd spend the whole time of LSST doing that survey, and you couldn't do any other science cases. So that would be true if you do a DESI in the north, or you could build a new spectrograph that matches D-spec for the Blanco for something like $40 million. For about $75 million, you could build a new instrument for an existing or funded 6 to 10 meter telescope. The cost difference between DESI and PFS is pretty small, so it doesn't really scale with telescope. It's scaling with things like the number of fibers and the number of mirrors, number of spectrographs. For $50 million more, you could rebuild a Gemini telescope to have a wide field. It would take that. Geminis were built to have small fields. So you could rebuild a Gemini telescope and have an 8-meter. You could do an instrument like this. Or you could just start from scratch, build a new telescope, build a new 8-meter telescope, build a new instrument in the southern hemisphere. There you're talking, $250 million. So that starts to get expensive. With a large enough coalition, maybe it's possible. And in particular, there are recommendations for things like this from a wide variety of sources. We have the Kavli report from the NSF. We have the Cosmic Visions report from DOE. In Europe, we have a report coming out on wide-field multi-object spectroscopy, really geared at complementing LSST and Euclid. Australia, in their decadal process, prioritized something like this. So the time seems to be right. There's a lot of people who recognize that the complement you want to LSST to do the science, to do the astrophysics, is spectroscopy, and to make a dent in the number of objects LSST will see, you need high multiplexing, you need wide fields. So there's a lot of compelling science cases for this, but right now there's not the money to make it happen. And my hope is that if we bring enough communities around the world together that all want this capability, at least hopefully we can make sure one thing like this is fully funded, and not be in the ELT case where we have multiple projects that are partway there, not all the way there. So if you're interested in this capability, please get in contact with me, stay in touch. We'll be working towards it as science book before the decadal survey. I think whatever your science area is, odds are it could benefit from something like an SSSI. And I'll also encourage you, these reports I talked about are public. It's well worth looking at least the executive summaries of the recommendations, so you can see where the field might be going in the next decade. Although we'll have a better view after the decadal survey of what's going to happen. So, thank you.
Okay, thank you very much for your talk. So we have time for questions. Okay, questions?
talked about a lot of instruments.
I have a
Yes.
question.
Yeah.
Hi, Jeff. Luis.
About a lot of
Luis here, Jeff. Just a quick question. I mean, as far as the dark energy collaboration in LSST, could you say a couple of words how it's organized, how it's funded, and how the
absolutely.
get in? Because, you know, I mean, we are in the process of selecting 10 PIs for Brazilian participation group, and we would like to know more or less how to proceed. Thank you.
Absolutely. So the Dark Energy Science Collaboration is a coalition of now more than 500 scientists around the world who are focused on preparing the stage so that when LSST turns on, we can do the dark energy analyses efficiently and robustly and have confidence that we're getting the right answers. So we're doing a lot of development now of pipelines. We're taking a lot of lessons learned from projects like DES to be able to analyze LSST data. We're analyzing simulations of LSST data. We're analyzing data sets like CFHT-LS that are being reprocessed with the LSST pipelines. The collaboration is focused around a set of probes. So there's a weak lensing working group, a large-scale structure working group, a clusters working group, a strong lensing working group, a supernova working group. There's a theory and joint probes working group that focuses on how do we combine measurements from multiple probes, what are the systematics we need to worry about. There's a set of working groups focused on computing infrastructure and survey simulations, working groups focused on sensor anomalies and how we deal with them, and photometric calibration. And so so Rachel Bean at Cornell is the spokesperson. She's been a leader in trying to secure resources from the U.S. Department of Energy. The intention is that countries will contribute in kind, proportional to their representation in the collaboration. So the U.S. Department of Energy, we're hoping will provide some funding for people to help scale pipelines up to the supercomputing needed for LSST, for instance. In the UK and France, there's funding for similar sorts of people. So we have not, we've talked about, but we have not gone the direction of charging people a membership fee or anything like that. So anyone with LSST data rights is eligible to join the Dark Energy Science Collaboration. And once they do, they get access to the wiki, access to the mailing lists. There's a category of full membership, which is what's required to basically have authorship rights on desk publications. That requires people to actually be doing work. So the 500 people, about 150 have made that full membership commitment, that they're putting a substantial part of their research time into LSST. But we expect as time goes on, that fraction will go up as we get closer and closer to data taking. Desk is open to people at all levels, from the most senior to the most junior. We meet twice a year. Our most recent meeting was in Oxford in the UK. Our next meeting is at SLAC at Stanford in the US. The one after that will be at Brookhaven near New York City. Let's see, what other sorts of things might people want to know, Louise?
A lot of information already to think about.
Yeah, so I would say go to lsstdesk.org. You can find the membership form, but also we have something called the Science Roadmap, which spells out the activities that we think we need to take in the next 3 years to be ready for LSST commissioning to begin.
So is that publicly available?
Yes, it's publicly available. It's on the website. So I'll try to compile all the URLs from this talk, and I'll add.
That would be useful. We could post that. You know that we have a website for the BPG specifically.
Good.
So we could put that there and help people. I mean, there is a deadline coming up February 10th for people to submit their proposals. So
yeah, so I think it would be very helpful to be able to point to how you fit into these plans,
yeah.
Where people can contribute. I think that would be beneficial. For
So
people.
what does Rachel do exactly? I mean, she's the convener of the...
So she's the spokesperson. So the spokesperson is kind of like the president of the collaboration.
Mm-hmm.
They handle all the day-to-day management of, the financial aspects, the management aspects. The spokesperson names all the working group conveners, for instance.
Okay, but that's just for the dark energy group.
Just for dark energy.
Okay.
So there's a set of other science collaborations.
Yeah, I mean, we've been talking to them and they've been making presentations. I just wanted to underline this fact that there are three very different types of organizations, in fact. There is the LSST project funded by DOE and SF, no money, just money for construction. And then there is the astronomy, let's call astronomy working groups that are looking for their own money through the LSST Corporation. And there is a dark energy group, the dark energy collaboration that it is like you described. So I just wanted people to understand more or less the organization. Thank you,
absolutely.
Jeff.
And right now, DESC is probably as large as all the other working groups put together. There's some overlap. But,
and of course, there are people from Dark Energy Survey, there are people from DESI, there are people from BOSS and eBOSS, right?
Yes.
So
oh, yeah.
everybody meets again somewhere else.
Yes, exactly.
With different hats.
Yes. We have had that. It's an issue sometimes because people have so many hats that it's hard to get focus on one thing.
Yeah, but clearly, I mean, the Dark Energy Survey is definitely a very good precursor of the LSST, right? I mean,
exactly.
In many ways.
Yes. Yes. And we have a number of leaders in DES that are playing important roles in the dark energy science collaboration for that reason.
Thank you, Jeff.
Any more questions? So I want to thank you, Jeff, again. So very nice talk. And thanks everybody for attending. And you also. Okay, and maybe someone can send you by email if they have any doubts.
Absolutely. I'm always happy to answer questions by email.
Okay, okay. So thanks everybody and see you all soon. Bye-bye.
Bye.
So Jeff, could you send me your PDF?
Of course.
Oh, okay, great.
Yes. Yeah. All right.
Okay, so thank you again and